Our first speaker today is Ray Salemi. He's in the Siemens Digital Industries Software Division, where he is the Aerospace and Defense Solutions Manager. The title of his talk is Using Python in Verification, and he's looking at his slide. He's going to be introducing Python UVM. So Ray is, as I said, is the Aerospace and Defense Solutions Manager for the IC Verification Solutions Division of Siemens Digital Industry Software. He's the author of FPGA Simulation and the UVM Primer. He's actually based near Boston. So thanks for dialing in early. Over to you, Ray. Thank you.
Oh, my pleasure. Okay, so as you can see today, we're going to be talking about using Python in verification, and we're going to talk about a package I've created called PyUVM, which is Python written in UVM. So let's, there we go. Okay, so basically we've made an assumption in verification that we're going to have a software, test bench software, that's going to use proxies to talk to drivers and talk to a DUT. And we think about that software as being written in System Verilog. Sometimes we think about it being written in VHDL, say with the UVM, but it could really just be Python. And so that's the inspiration here. Instant question you get is how are we going to connect Python to our simulator? And there's a variety of ways. There's the VPI and the VHPI and the DPIC and the old PLI probably. But what we're going to use here is we're going to use CocoaTB to make the connection, and that's a coroutine-based system that uses the VPI or the VHPI to talk to the signals in a simulation. And so we create a proxy in CocoaTB with function calls to it, and then write a Python UVM test bench on top of that. So what's so great about Python? Why would anyone want to use Python? In fact, I'm looking forward to the talk later about why we shouldn't be using Python, but here's why I think we should be. Python's a much easier language to deal with than System Verilog in many ways because it has no typing issues. Everything in Python is a handle to an object. So we see here, for example, that AA is an integer holding 6,000, BB is a float holding 1600, but I can say BB and put an AA, and I don't get any sort of syntax error because all that's happening is the handle to the float is going into AA. And this integer, which is an object in and of itself, gets garbage collected away because of this. And this causes us not to need these parameters that are all over the place in System Verilog and UVM framework. We can just put things in things and be done with it. Another nice element of Python is that it uses forgiveness instead of permission, and that gives us duck typing. And duck typing is if something walks like a duck and it talks like a duck and it quacks like a duck, okay, well that's a duck. And we don't have to get permission to say, is this a duck? Let's examine this duck. I think it's a duck. You just use it. So for example, we see here an example in Python down here where I have a little port and I put 100 into it. So 100 is an integer. I get the 100 out of the port and put it in II, and then I tell the integer to migrate, and I get an error. It says an integer can't migrate, and that's duck typing. I tried to make this thing do a duck-like thing. It couldn't do it. Well, go debug your code. There's no need to have the compiler checking all this in advance. So PyUVM is the UVM written in Python. I just went through, and there's another one out there called UVM-Python that you'll see on GitHub. That is a conversion with a script from the System Verilog code to Python. This I just went through the spec point by point and implemented what I saw there and what I thought was best implemented in Python. You'll see there are things I didn't implement, things that could be implemented in the future. But this is a Python UVM. And so here you see it in action. We have a class, an ALU agent. You'll notice that it extends UVM agent. I preserved all the names from the spec, so it's not UVM agent in camel case like in Python, but it follows the names you'd see if you read the spec. We have the phases, but we don't pass in the phase variable anymore. I refactored the phasing, and so we don't have to deal with that. Also, there's no macros. Everything in the Python UVM automatically is registered with the factory if it extends UVM void. This gives us a simplified way of using the factory. We just say class name dot create. There's no colon this, colon that, colon type ID create. You just use it directly. The same thing with the config.db. It's simpler, and you can just do a config.db get. In Python's, the system will raise a UVM config item not found exception if the thing isn't there. So we're not doing that if statement and then checking for a 1. We just handle the exception if it happens, or we don't handle the exception, let it go to the top and stop the program, whatever works for us. If we look through what's been implemented, the PyUVM implements the base classes, so UVM object. It implements the reporting, but it uses logging. It doesn't. I didn't rewrite UVM reporting because Python has logging and it's very good. So we'll just use that. There is some support for logging built into the hierarchy. The factory classes, as I said, work the same way, and UVM void, everything that's a UVM void is automatically registered. Simplified phasing, it only does the common phases, it doesn't do custom phases. Common phases are defined in the spec, and they're your favorite phases that we've been all using for everything. We have we implemented the UVM component and the behaviors in there, and also UVM root as a singleton, and then the sequencers and the sequences and the sequence items. That's all in there. It's just been refactored. I took what was in section 14 and 15 and just figured out what it was supposed to do and did it, rather than trying to go section by section, because it was very complicated and it was like a giant jigsaw puzzle that maybe would work at the end, and if it didn't, how would one debug it? So I did this, refactor the behavior. The things we ignored, like I said, was custom UVM phasing. There was no need for the UVM resource DB because no typing. There were no imp classes needed because Python has multiple inheritance. And as I said, we didn't do the reporting. I have not yet done, I think synchronization classes need to be done, but container classes, recording classes, transaction recording, things that were related to being in the simulator in a simulated language were left out. In the register layer, that could be done as an open source project in the future. So here's the factory in Python UVM. You can see rather than the long incantation here, we just do .create, and then the rest works the same way with the overrides and the instance overrides and the type overrides and the name overrides and all of that. The config.db, again, you just say config.db. This is a singleton. In Python, you don't have this get business where you do a get to get a singleton. You simply make the same call the first time you call a singleton and all subsequent times. So this config.db with the parentheses could be creating a new handle, or it could be getting the previously created handle. It doesn't matter to us. We're just using a singleton. And so you call config.db with the parentheses get, pass it the label and whatnot. And all of this works the same way it does in UVM with hierarchical overrides and whatnot. The PyUVM uses threads to handle concurrency, and threads in Python are a little different than they are in System Verilog or VHDL, where they're processes. Those languages are comfortable destroying threads at the end of a simulation run. Python won't do that. Python requires you to notify the thread that it's about to be killed and let it put its affairs in order and leave on its own terms. And so the way that's handled here is when you have like this UVM queue, there's a singleton called an objection handler that receives all of the raise objections and drop objections. When all the objections are dropped, then run phase complete returns true. So, so this loop loops in this UVM queue for as long as we're in the run phase. It does a get. This is a queue, so this does a get, a blocking get, but it times out, and it times out, and if it times out, it raises queue empty, which it actually just passes and goes back to the top of the loop and checks again. And we'll also see this can be also handled in managing clocks with the same pattern of not blocking, just flat out blocking, but blocking with a timeout and a check. Otherwise, you could just block the whole simulator and everything stops. Here are the common phases. This is an actual list in the code. There's the top-down phase and the bottom-up phase, do the things you expect them to do, and the code just loops through these phases, running all of them in all of the instantiated components. Logging, we use Python logging instead of UVM reporting, which is kind of nice. It makes a little more sense in some ways. There are logging levels as they are in the UVM, but the UVM has this thing where if you want something to be more likely to print, you give it a lower number, and then when you're running, things have to get under the verbosity ceiling in order to be printed. Python is a positive way of looking at it. If you want something to print more often, you give it a higher number, and things have to get over the level that you give them there. And the FIFO debug messages have been added in, so when you're trying to debug your test bench, you can see what's going in and out of the FIFOs. Here's logging in action. Every component gets a logger named self.logger, and then you just call debug info warning error critical. It prints them out, and I modified the format so it looks kind of like the UVM reporting, but it has the path to the component instead of the message ID, because message ID is not implemented. And we can control logging with a set logging level on a report object, and in a component, set logging level hierarchically, and this does the same as in UVM. It sets the level from there down through the hierarchy. We can also change the handler. The handlers say where the logs go. There's a stream handler that prints to the screen, a file handler that writes to files, and there's even a null handler that does nothing. So here's a quick example of this in action. We have the tiny ALU. This is the UVM primer example design, and it has a driver with a sendop function. It has a monitor that monitors the commands and looks for the start signal, and you can do get command to get the commands in the order that they're seen. On the result side, we monitor the done signal, and you can call get result to get the results in the order that they're seen. And you can actually create a whole test bench without a simulator, right? You create a Python proxy that implements these function calls, and you can model your DUT in Python, write your test bench in Python, run the whole thing in Python, and then when you have something to simulate, you can switch over. So here we see there's a Python proxy that I just spoke about, and our CocoaTB proxy. And the CocoaTB proxy puts itself into the config.db so that the Python, the PyUVM code can get it. Monitor. This is a monitor class, and one nice thing about this class, you'll see here in the run phase, it is passed, when it's created, it's passed the method name. Is this a get command monitor or get result monitor? You can write one set of code and pass the string that's the name of the function that you want to call. And Python allows you to do this get attribute command to pull out the method with that name and then call that method. So it's easier to write code that doesn't have to be copied and changed in a minor way because of the function name is different. This is the BFM written in CocoaTB. It's an asynchronous coroutine. Falling edge coroutine, a weight falling edge, comes from CocoaTB, and we loop on the falling edge, checking the done signal. And when done goes high, we put the result onto the monitor queue. Then someone can call get result, and it will block until there's data in the queue. For functional coverage, in this case, I just created a set and I put every operation I see into the set. And then in the check phase, I take the set of all operations and subtract the operations I've seen. And if that's greater than 0, I print out the ones that were missed. Sequence item is, we don't implement do compare or convert to string because there are Python equivalents for that. There's the under equal, under magic function that we call, so that works with the equal sign. And the under string under works with print and anything else that converts any object to a string. So we use Python where we can to do this sort of thing. And I wrote randomize myself. We created an ALU test, which is the base ALU test. It creates the environment in the build phase, sets the logging level to debug, and then in the run phase, it raises the objection. It gets the sequencer. It creates a sequence. It starts the sequence with the sequencer. It sleeps a bit, and then it drops the objection. From the base, we have a Python ALU test that uses the Python proxy, and a CocoaTB ALU test that actually leverages all the code above, but adds a final phase where it uses the proxy to tell the BFMs that it's done running. And then if we're just running this in Python, we have this if name, and it runs Python ALU test in Python. So here we see CocoaTB owns the test and runs the test. It runs the clock. It instantiates the proxy, and then puts it in the config DB. It has these asynchronous BFMs, and it forks all of these off so that they're running. We wait a clock just to make sure they're going, and then we launch our test in a thread, and then we wait until the test tells us that it's done. And that's the code running right there with CocoaTB. CocoaTB is available on pypy.org. You can do pip install pyuvm, and pyuvm is on GitHub at GitHub pyuvm. And I'm Ray Salemi. I'm the Aerospace and Defense FPGA Solutions Manager, and you can contact me at ray.salemi@siemens.com. And now I can answer questions.
Thank you very much, Ray, and thank you for getting so much content into a short time. So we do have 4 minutes left for questions, so I'll go through some of the questions, Ray, that have been raised with us. So is it possible to interface a new Python verification environment with an existing system Verilog UVM environment?
Well, you can do anything with DPI at some level. And so one can always make that sort of connection. I imagine what someone is asking is, can I have a system Verilog test bench that's running that somehow the Python can interact with? Well, the system Verilog can reach out to the Python. It's harder for the Python to reach into the system Verilog. But I haven't fully explored everything DPI can do in that regard.
Okay. But you're suggesting DPI might be the way to do it?
That's the way it's going to work, yeah.
Okay. Then, do you support constrained randomization?
There's no way that this code yet accesses the constraint solver that's in Questa. There are a few packages out there that do constrain random in Python. They're not as fast, of course, as the constraint solver in Questa, but there's something called PyConstraints out there that one could try.
Okay. So is this available on a GitHub project?
Yes, it's GitHub/PyUVM/PyUVM, and it's open source and it's up there right now.
Okay. Okay. And then, so how much of the UVM is actually been implemented? For example, is coverage not implemented yet? Is there a plan for coverage?
Well, coverage is a system Verilog thing versus the UVM thing.
Yes.
In this presentation, I did coverage with a Python set. I think that it would be interesting to see if we could find ways to interact with the UCDB, which has an API, and we have the ability to access C. So one could imagine some sort of coverage package in the future, or in a future version of PyUVM.
Okay, and then you'd you'd write the information to a UCDB format.
Right.
Okay. Okay. And have you done any performance characterization in terms of Python versus a fully implemented UVM environment in some of the simulators?
I have not done that. And so anyone else's guess is as good as mine. My instinct suggests that the RTL always is running a little slower than the test bench software. And I would be surprised to see a test bench slow down because one switched from System Verilog to Python, especially if you're using NumPy or one of the other big computational elements in your, say, your predictor.
Okay. Okay, and just I think the last question, does PyUVM support only Quest, or does it support other simulators too?
Oh, it's independent of simulator. In this example, it's connected through CocoaTB, and CocoaTB supports all the simulators that I can find.
Okay.
But one could also imagine connecting it through DPI, and it could talk to Veloce, it could talk to Questa, so
Okay.
it can do all the simulators.
Brilliant. Okay, and that's out of time, so there's quite a lot of questions, quite a lot of interest, but I guess people can access PyUVM directly. So thank you very much.